So y x will be 0. So if I put an incident wave, something will get reflected and something will get transmitted. My job is to find out how to uh, how to obtain. Uh, Go to the next slide. Now, in the Maxwell's equation, put dou x is equal to dou y is equal to 0. And using that, once I put that, using that, I can discretize. My discrete equations will be on the right hand side. So dou z ey minus dou y ez, uh, that will be modeled like this. Because dou y will be 0. So ultimately, dou y ez will go out. So the first line will become dou z ey is equal to mu x or mu y c0 dou t hx. Now I know how to discretize both the sides. So discretize both the sides. Similarly, for the second one, dou g ex is equal to mu y c0 dou t hy, discretize both the sides. The equations are given. And the third equation is actually both the sides are 0. There is no variation in y or x. So left side is 0 and there is no hg. Since we have hx or hy, either hx or hy. So there is no hg. So third equation is 0 on both the sides. So I get two equations now corresponding to two discrete equations corresponding to two Maxwell's equations. Now I will take only one of them later. Next. Okay. Now, so that once that is over, then we can find out for the time derivative of E. That we did for time derivative of H. Now let us do for time derivative of E. So from time derivative of E, similar procedure, same equation, similar equation. And now we can have two modes, Ex, Hy mode. Either Ex and Hy are present, or Ey and Hx are present. So these will be two modes corresponding to these two modes. The discrete equations in E and H will be are shown here. I'm not going into that anymore. Let me come to the, just remember that these are the equations that we are going to follow. Okay. So let me start with this EYHX mode. I'll skip the other mode when it will come, but the EYHX mode I will take. So how you to formulate it? Starting equation is Ampere's law in EY. So take this equation. From Ampere's law, we get this equation. So we'll take this equation from EY. Rearrange this one and solve it for future time, which means T plus delta T is the future time rate. This one, T plus delta T. So take that onto one side and put all other terms on the other side. Go forward. So ultimately, the last equation we get. Now, if you look at the last equation, Ey left is evolving value, or it is the present value of Ey, so that is not a problem. Then the term within the bracket C0 is constant, delta T we have fixed, so that is constant. Eyy is also constant at a value k. Delta Z is also constant. If we have fixed that, delta Z is also constant. So being that within the bracket. Now what you have to do is, so since all those are constant, before we proceed with the FDTD loop into a for loop, beyond the for loop, before the for loop, calculate a value for this constant. So take a new value for this, give it some name and calculate it before going into the for loop. We'll show that later. So this is update for EY. Similarly, similar procedure. Here you will start from Faraday's law and go to update for HX. The equation will be here, same as in the previous case, and same logic applies. What we discussed, same logic applies here. So next. So now, as I told you, the coefficients will be constant. So therefore, they remains constant during the simulation. Compute them only once at the beginning of your program and keep them for use in the MATLAB FDTD. Now, FDTD those equations are given below. Last line. So the last line gives those two equations for material parameters or material coefficients, MEY and MHX. So those two are calculated earlier before we go to the FDTD loop. Next. So that we will use in the FDTD formulation. For FDTD formulation, what we do is we use a Gaussian source for excitation. Region is simply approximation impulse, and impulse contains a broad band of frequency. So if I do that, if I use a Gaussian source and finally take a Fourier transform, then I'll get the result for all the frequencies. With one simulation, I get result for all the frequencies. Unlike frequency domain solvers, where for each frequency you have to simulate it once. For each frequency requires a renewed simulation. And you know what is the form of Gaussian source. I'm going here the source Gaussian source for tau is equal to 0.5 by f max. Remember this. This is a tip that you have to take tau is equal to 0.5 by f max and t0 is equal to 6 tau. These are two tips that people have gone from their experience. We use that to simulate the Gaussian pulse. Then I have to find out what is the estimated iteration number. Total simulation time t will be 12 tau. I told you how to calculate, plus 5 t pop. I said t pop is equal to ng into n max delta z by c0. That is across the grid, one time into t pop will be this. So that is the time it takes for the wave to propagate over one grid. So from that you find out this. So that gives you the total simulation time. Total number of iterations that you have to find out. So that people call NT, or some people call steps. So that is steps. So steps will be time and total time it requires divided by delta t, rounded up in the upward direction, or here you can use CL function exactly as in the previous case. So this must be an integer. Steps will be integer. So once you know what is the number of, once you know what is delta t, now you can fix what is, and you know what is the total simulation time, then you can find out how many steps. So that is done. Then I think, madam, should I stop here? Coding, if you permit me.
Sir, are you able to continue? Are you able to continue? Then okay, sir.
Okay, all right.
Okay,
I am able to continue.
Okay,
So,
sir. Okay.
Okay, there
Yes,
is. Okay, so let me continue. Give me 1 minute break. Let me take some water. Then I can continue. Now, in a typical scenario, what happens is we have an object, scattering object, or you take your antenna, take any object. It is illuminated by a source. So even if you are exciting an antenna using a transmission line, it is actually antenna is illuminated by a source from which the power is coming through transmission line to the antenna. So it is illumination of the source. Then once it is illuminated, then it scatters. So antenna will radiate and something will go back, get reflected, something will get radiated from the antenna. If you have a normal object. So some scattering object is there. There will be a source. From the source, EM wave will come to the scattering object, get reflected, get transmitted, get reflected and transmitted through the object. So there is a typical problem. This is called a total field scattered field framework. It is a typical problem. Typical problem is that the source, the side where your source is there, that side also will experience reflected wave or scattered wave, which are transmitted through the object. They will pass away. There is no problem. But others, there will be uh, an interference between the reflected wave and the source. So that is a typical problem that can happen. And this is called a total field scattered field framework. Total field is the reflected field plus the incident field. That is the total field. So that will be over a region only. Beyond that, because what's the source? What is one? Suppose source is located at Z is equal to ZS. So if you pass ZS, when the reflected beam goes past ZS, then there will be no source. So there will be no uh, incident field. So since there is no incident field, there is no question of total field. It is only scattered field. So beyond the source, it is only scattered field. Between the source and the object or the scattering object, this zone, you can have scattered field and reflected field, so that is total field, and beyond the object you will have transmitted field. So these are three typical situations or typical zones that we are required to handle in our FDTD coding. And that gives rise to a typical problem. The boundary beyond which there is only scattered field, and the boundary in which and the everything before that boundary where there is total field, that creates a problem in formulating the FDTD. The reason is in the FDTD, as I told you, as we saw, that we are taking grid points, and some grid points will be within this file total field side. Some grid points will be on this scattered field side. Now, at the junction, once you reach the junction, there if you are going to update the field from the total field side, that field will depend on the scattered field side, which you do not know. Similarly, if we are going to update the field in the scattered field side, that will depend on the field of total field side, which you do not know. That creates a sometimes problem. That is what I am showing here in the second picture, right hand side. The grid points are shown. The solid points are for source side, and just hollow points are for the scattered. So source and total field is there in the solid, and scattered field are there in the hollow side. There is a difference also. At that point, K SRC and K SRC minus 1. These two are critical points in formulating the problem in such a situation. Now, don't confuse with this K. This K is like IJK, which means I cap is a unit vector, J cap is unit vector in Y, K cap is unit vector in Z. This K is similarly indexing term for the J. It is not the wave number. This is the indexing term for J. Please remember this. Don't get confused with this as the wave number. This is the indexing term. Go to the next page. Now look at what is happening. What happens here? On the SF side means source field side. On the source field side of the interface, H field in the FD equation, that will contain a term from the TF side, total field side. This is because of the staggered EMB. Now, what is the update equation at that point? Update equation is Hx, which is shown in the left side, at ksrc minus 1. That will be Hx ksrc minus 1. So those are all in the TF side, sorry, SF side. Then material parameter is multiplied, so that I am not concerned. Then look at the rate curve, Ey ksrc. This is in the update equation, normal FDTD update equation that gives us this. The Ey ksrc. What is this ksrc? This is in the uh, other side, in the total field side. ESRC is in the source side, so is the total field side. Minus Ey ksrc minus 1. So that remains it is as it is. So this is the complete picture. Now, how to handle this? This is an equation in the scattered field, but EKSRC, this is a total field quantity. How I am going to handle it? The solution is simple. Subtract the source term. Don't subtract the field value. Subtract the source term from the KSRC. KSRC from that, subtract the source term. That makes it look like a scattered field. Because what is that in that total field side? Total field is equal to source plus reflected. Sorry, source plus scatter. Right now, if I take out the source, then I will be left with only scatter. So subtract the source term. So that is the solution for that. So take out the source term from that. Right? And so this shows the formulation. So what I have done is the green point shows the source term is subtracted from that. So it looks as if we are doing the normal FDTD operation with the final right hand side last equation being last equation that is subtracted, the source is subtracted from that. So normal FDTD operation up to that point, up to the SRC minus 1 point, whatever it is, do it, then subtract the source from that. That will give you the field value in the total. So then the same thing will occur for SF side, scattered field side of the interface, if we are considering the E field, while we are considering the E field. So in this case also, same thing. Instead of subtracting here, you have to add the source term from the SRC. Add the source term. By adding the source term, will solve the problem. As I told you, total is incident or source plus reflected or scattered. Right? Total is source plus scattered. Now, I don't have the source here. I have only scattered, but I am looking for the total. Therefore, I have to add the source. If I add the source, then I get the total. Then everything is as before. So that will solve the problem. So these are two tricks that we use at TFSF solutions, or which we call TFSF correction. Okay, this shows the exact mathematical expression for that. Okay, let's go to the next one. Then comes some another concept which is called the two source term. Two source terms. Now, what happens here is before we go to the main FDTD loop, we calculate the two source functions. There can be two sources. One is for electric field source, one is for magnetic field source. So you have to calculate both these source functions before you go to the FDTD loop. So if you are using only one source, then calculate that source only. If you are including both the source, calculate both them. But before you go to the FDTD loop, don't do the calculation within the loop. That will unnecessarily take more time. You will get into problem. What is to be observed here is the amplitude of these functions can be different. H and E, their amplitudes are different. Functions are half grid cell upper, therefore this is important. They have a small time delay between them and they exist at different time steps because they are in time step also they are half time step upper. In the grid they are half grid upper. In time step they are half time step upper. So you have to calculate both these. This is an observation. Okay, let us see at least one of these. This is equal to Gp. Electric source is equal to Gp. Gp, as I told you, is the Gaussian function. How to define Gaussian function, we know. Now, once I know the electric field, then I have to calculate the magnetic field. So magnetic field will be Hy. That will be calculated using this function. Hy will be minus root over of epsilon upon mu. That you know why that comes. That is because H is equal to E is equal to eta H. So from that we get this. So Hy is minus of that into G. Then plus y there plus NSRC Z delta Z by 2 C0. That is for the difference in the grid position. Then half time apart, therefore plus delta T, right? So that takes care of the half time apart. And in the middle term, you see 1 by 2 term is there. So half grid point apart is also taken care of for H1. Similarly, for the other one, start with the same thing, EYSRC. Here you started with EH, there you start with EYSRC. Otherwise, the formulation is same. These values, these mu SRC, epsilon SRC, etc., beta RSRC, these are the material properties at the injection point. Injection point is where we are giving the excitation in the grid. So the grid point where we start give the excitation. We put the Gaussian excitation at that point. Now, one thing is to be remembered that this Gaussian pulse must come easily, ease its way into the grid. Suddenly, if it appears there, then there will be a problem. We'll see that later, but then there will be a problem. So it is to be designed in a manner that it eases into the grid. Now the boundary conditions that I am considering this Dirichlet boundary condition. This is the numerical Dirichlet boundary condition, not the physical Dirichlet boundary condition. In the numerical Dirichlet boundary condition, when we implement this, we assume that all field quantities outside the grid are zero. That is the first assumption and most important assumption for this. Then we modified the update equations using this assumption. So using these assumptions, if we modify the update equations, we can see these four equations. These are the modified equations. After assuming this Dirichlet boundary condition that outside grid everything is zero. The first one you can see why this is true. In the first one it is k less than ng. Second one k equal to ng. So beyond ng everything is zero. So we are making everything zero beyond ng. In the third, fourth, k is greater than 1, k is equal to 1. So beyond k is equal to 1, everything is 0. So on both the sides of the boundary, we are making sure that everything, all fields are 0 beyond the boundary. So within the domain only field exists, and we are calculating the field within the domain. Yeah. Okay. The PABC I have told you what is it. Now the question is how to implement it. So to implement it, choose the time step of the physical way to travel one cell in 2 time steps. So this is how you choose the time steps. So delta t is equal to n delta z by 2 c0. So this is accordingly you have to fix your delta z so that current condition is also simultaneously satisfied. So to do that, once that is done, then implement on the left hand side of the Z boundary and implement on the right hand side of the Z boundary. So to do that, I define a small quantity h1, small h1, little h1, which is equal to at t plus delta t by 2 and k. And similarly, ey, then you can update using this value of hx. We can update ey at the boundary 1. So ey at 1, that boundary condition is there. So at the boundary z is equal to 1 or k is equal to 1. So ey 1 is the boundary. Then t plus the right hand side, all k is 1. So put all k 1. Then in the bracket you can see that we have to use two h values. One h value is there for 1. The other h value is given by this h1 or h2, whatever you write. So h2. Similarly, we can modify the h field update equations at the right side boundary. So if I do that, then we get this modified equation for ey also. Once we get modified equations for hx also. So we got modified equations for ey and hx at the boundary using the perfect observing boundary condition. So this is what I am going to implement when we go through the MATLAB programs that are using that we are going to use here. Go to the next slide. Then, as I told you, we can everything is done in the time domain. Then we have to go to the Fourier domain. So for Fourier domain or the frequency domain, we have to take a Fourier transform. So find out, use the usual Fourier transform. If you can do that, if you have a program for that, use that. Otherwise, if you don't have the program for that, at different points of time, hx at different points of time. So at different times, you are getting e and x. So those are at discrete points. Then approximate Fourier transform using this. What you learn from DSP, digital signal processing, we know how to do this. So you'll find out what is f of f. Here m is the total number of time steps. Small is small, m is the time step. Now to implement this in the program, put this ff as this value in the program. Write a code for that. I'll show you the code later. Put it in this value, this curve. Let me tell you how to do that. After the end of the main executive loop, I have to implement this f of f, which is given by this expression. Delta t is summation of exponential term of something to the power m into fm. Now delta t, this is a multiplication which can be done outside the main FDTD loop. Reason is it is not going to affect the FDTD algorithm at all because delta t is fixed. So there is no point in putting this within the loop. Then the last term, fm, these are the field values of interest at the current time. And in the middle term, this is the kernel. This kernel is to be put before the main FDTD because there is nothing which is useful within the FDTD loop. So everything will be repeated. If I do that, so that calculation will be repeated. So before the FDTD loop, put delta t, find out what is delta t, find out what is the kernel value. So keep them in one D array. Then within the FDTD loop, because you are going to use FM, so FM will be FM you have obtained from the FDTD loop already. So that bring it in and put it in this. Then post-processing, once Fourier transform is done, then what we have to do is normalize the spectra to calculate transmittance and reflectance. How to do that? Divide the reflection and transmission spectrums by the source spectrum. So that gives you the reflection coefficient, transmission coefficient in the Fourier domain. Then it is a good practice that you add them together. Reflection and transmission, when they added, they should be 100%. They should give you 1. Otherwise, there is some energy addition from some sources if it is more than 1, which is not possible. Conservation of energy is violated. If it is less than 1, then energy is dissipated. So don't do that. So it is always a good practice that once you complete your programming, check it whether energy is being conserved or not. Unless you are using a lossy material, specifically you are using a lossy material, and then you check this CF should be added plus TF plus MF. MF is the loss in the material. So that should be 100%. So that is a very good practice for these things. Now let me outline the steps of the Dtd analysis. Then I will stop. Program, if you allow me tomorrow half an hour, I will show you program. Today I showed some program. Tomorrow I can show you the code, complete code for one example, a Dtd example, complete code with explanation. It will take about half an hour. What I will feel, I have started feeling tired, so I do not want to continue beyond this. And the steps are, the 4 steps are there. There are 4 steps. First step is the definition of the probe, which is the device that you are going to model. So first find out what is the device, what is the characteristics of the device, electrical characteristics as well as physical characteristics, length, width, etc. Then dielectric constant, magnetic constant, conductivity. So all those things first find. Then what is the geometry, what material it is made up of. So all those things come. Then what do you want to learn about this device? You want to find out reflection coefficient. You want to find out gain. So that is what you have to do. So first you define the problem. Second is initialize the FDTD. So for initialization, this is the last slide. For initialization, compute the grid resolution. Then assign the materials, those values to each point on the grid. Once you have done the grid resolution, compute the time step, that is the next step. Then initialize the Fourier transform. Then run the FDTD. Finally, post-process, in which you will find out, or you will do the Fourier transform. What is your R, what is your T, and from that, all other requirements. I think I will stop at this point for today. I get, if you allow me tomorrow, half an hour, maybe I will.
Okay, sir. If you're feeling tired, we will discuss the remaining topics tomorrow, sir.
Yes, yes.
Dr. Perimal, sir, will let you know the timing.
Okay. Okay.
Sir.
Yes.
Sir, I am Perumal Shankar, sir. It is a very wonderful lecture. Even for teachers, we learned so many things from you, sir. It is very much required for the people like me. So those who are working, and mathematics is very important, and it is a fundamental, and you have explained everything, even up to that, all Fourier transforms, Fourier series, everything you have explained. That is very nice, sir. Very nice. Thank you. I learned so many things from you, sir, today. We need one more lecture like this, sir.
And
Thank you.
I'm Raghavan. Now,
please, sir. Please.
I would like to get official permission from the coordinator that.
No, sir. Sir, no, don't ask such types of these things, sir. Because you are always you are always you having the right to do all the things, sir. You are the mentor of the whole talkage. Everybody, that is including our beloved HOD as well as principal, they are having very much good opinion about you, sir.
Thank you. And Dr. Mishra and myself had a talk in the afternoon, and during my talk, I have 2 hours on Saturday. The last half an hour, Dr. Mishra will be enlightening the participants. And this is the second time Dr. Perimal Shankar is openly told. The first time is when Jones explained the demo software. And this is the second time he is openly told. So that shows how much involved he is in mathematical way, that too in MEMS. So the credit goes to Dr. Rabindra K. Mishra, who is a role model to the whole world. Yeah. Calamity is not a lame excuse for not improving the technical ability. There is no person in the world like Dr. R.K. Mishra, who is not bothered about any kind of calamity. It's a lesson for all of us. Thanks a lot.
Thank
you.
My voice
Thank you,
is,
sir.
uh,
Thank you, Devendra sir. Thank you,
Madam,
Devendra.
Sar is telling something.
There
Yes,
are
yes.
questions. I'm sorry, I cannot take it now. Because if I speak, you cannot listen. It is completely dampened. It will go down. Attenuated a lot.
Pardon, sir. Pardon, sir.
That is the problem. Am I audible? I have to.
Yeah,
start
Now
no,
it is audible. Now it is audible, sir.
Yes, now I am struggling to speak. That
Okay,
is why
sir.
I am saying that questions I will take. Either you send me, I will send you the emails, or in the email I will reply, or on the Saturday, or tomorrow when there is a break. Anytime I will take the questions, please. Note the questions, I will answer definitely all the questions.
Okay, sir. We will discuss questions tomorrow, sir.
Yes.
Yes, sir.
My throat is giving some problem.
Yes, sir.
Sir,
Yes, sir. You take
please,
rest, sir.
I
Sir,
had
please
an
take-
operation into my neck, my throat.
Yes,
There
sir.
was a cut in my throat. So after
Okay.
some time, it gives problem.
Okay, sir. Okay, you
Sir,
take
please,
rest, sir.
sir, please take care about your health, sir. Please take rest.
Yes.
Okay, sir.
Thank you, Devendra sir. Thank you very much, sir, for sharing your profound knowledge with us. Your session was full of real and valuable information. Even though you are not feeling well, sir, you are here with us for whole day. The entire Tokesh team appreciate your sincere effort for making this session a grand success. Get well soon, sir. Thank you, sir.
Thank you, everyone.
Pinamar sir, can we wind up the session?
Yes, ma'am. Yes, ma'am.
Yes. With this, we are winding up this session. Thanks to all the participants for your active participation. And special thanks to Raghavan sir, Rabindra Mishra sir, Sudhagar Rao sir, Mahadevan sir, Lakshmi Narayana Mirgu sir, and Shyam Sundar Patnaik sir for your constant support and encouragement. And thank you, Perumal sir, for coordinating all the activities. And thank you, Dr. Diba Elizabeth George, HOD Department of EZ. She is always with us and she is our backbone. Thank you, ma'am. Thank you, Dr. Gnanashila Miss, for your guidance and support. Thank you once again. And we shall meet again tomorrow morning. The first session scheduled at 9:30 a.m. on the topic Flexible Antennas, Design and Implementation by Mr. Dundi Kumar Janpala, Senior Research Fellow in DRDO funded project.
Thank you,
Thank
madam.
you.
Thank
Okay.
you.
Raghavan sir, are you there? Raghavan sir?
Madam, our mic is muted. Okay, madam.
I think mic is muted, sir. Okay.
Okay.
Okay, sir.
Thank you all.
Okay. Thank you all.